Hi, this is Leanna from period 5, and we're going to do some easy problems, number 4, 5, and 6. So here we go, number 4. An 80-kilogram person stands in an elevator. So here's our elevator and our person. Our system is going to be the person. And it's moving upwards with a constant speed. Constant speed. Acceleration is 0. So that means that the net force is 0. And we have the mass, so we can find out the weight using this formula with the 10 newtons over 1 kilogram times our mass, and that'll equal our weight, the weight of the person, 800 newtons. And because the net force is 0, that means that the sum of the net forces acting on our system, the person, is going to be 0. So in this problem, there's only normal force and weight acting on the person as forces. So if there's 800 newtons of force as weight, that means there's also got to be 800 newtons in the other direction. So the net force will equal 0. And actually, I was supposed to draw a vector sum diagram, but it would look like one arrow going up, and that would be the normal force, and another arrow coming down, which would be the weight, and they would be equal in length. The vectors would be equal. Okay, so now we're going to move on to number 5. An 80-kilogram person stands in an elevator while it speeds upwards. Speeds upwards. It's moving up, and that means there's acceleration in this direction, upwards, at a rate of 3 meters per second so that's 3 meters per second squared. And again, our weight is going to be the same as the previous problem. It's going to be 800 newtons because our gravity field didn't change, and neither did our system's mass, which is the person. And so we have to find the net force, and we do that by using our equation mass times acceleration. And our mass is 80 kilograms, that's the person's mass, times acceleration, 3 meters per second squared, and that'll give us 240 newtons, which is our net force. And if we draw a vector sum diagram, we'll see that there's, let's take a step back first, because we usually draw the force diagram first. Okay, so at this point, we can only say that there's two forces acting on our system. There's the weight, and there's also the normal force from the elevator pushing upwards against the person. So we know that the normal force is going to be longer than the normal force vector is going to be longer than the weight, because because the acceleration is going in the upward direction. So we draw our vector sum diagram, and we show that normal force is longer in length than our weight, and then this fat arrow is the net force. So our weight, 800 newtons, and our net force, 240 newtons. And if we add those up, we'll get the normal force, 1040 newtons. So I remember going over in class something really cool, like what is the person actually feeling as the elevator is accelerating upwards and the normal force is pushing up against the person? They're going to feel really heavy. That's what we concluded in class, because our brain gets confused, even though our heaviness should be associated with weight. Our brain actually associates it with the amount of normal force pushing against us. So yeah, our brain's stupid. Okay, next problem. Oops. So an 80 kilogram person standing in an elevator while it slows down. Okay, so now it's basically the same problem as before, except now our acceleration is in the opposite direction. It's going downward at 3 meters per second while moving up. Okay, yeah, so even though the motion is still upward, the acceleration is downward, so the velocity is in one direction while the acceleration is in the other, and our motion is slowing down. But we don't really know that. So let's continue. So our weight is still the same. Gravitational field still on Earth, didn't change. 10 newtons over 1 kilogram times the mass of our system, our person, 80 kilograms. Okay, and then we get our net force equation again, mass times acceleration. And lo and behold, it's the same as the previous. But let's look at our force diagram. Instead of our normal force vector being longer than our weight force vector, it's the opposite now. That's because we're moving downward, or not moving downward. The acceleration is going downward. So we have kind of more force in a downward direction. Let's look at our force diagram here. Not vector sum diagram, I mean. So our weight is 800 newtons, and we have the normal force. Okay, we don't know the normal force yet. Cross that out. And we know our net force is 240 newtons. That leaves us with this area over here, the normal force. And we just subtract 800 minus 240, and it's logical. You get 560 newtons for this area, for this length, because it should equal the vector for weight. But as you can see, we are still, actually this is a little weird. Still moving up, but the force is, the net force is going downward. Well, if we had put a negative sign on our acceleration, we would end up with a negative net force. So that is possible that our net force could be negative, but we're still going in the other direction. Just like you can, even though acceleration is one way, you can still be going the opposite way, just slowing down. So it makes sense. So what this person is feeling as the weight is bigger than the normal force acting on the person, they're going to feel, let me see, they're going to feel pretty weightless, because there's not as much normal force acting, pushing upwards. And like I said before, the brain gets confused and associates normal force with heaviness. And here the normal force is lighter than the weight. So this person's going to feel weightless moving upward. Thanks for watching.